This is a low noise amplifier with 5 junction FET transistors in parallel. It is the J310, 5 of them. Then there is a massive decoupling of the supply voltage, because I'm interested in low sideband noise at close frequency separations. Here is the schematic diagram. I'm using noiseless feedback with iron-free transformers. So the input coil is 22 turns and then 11 turns to ground. So it's a step up of the voltage by a factor of 3. And the feedback winding is 4 turns. On the output side I have about half a meter of trifilar wire. 2 windings in series on the drain side and 1 winding on the source side. And then the output is taken from the drain. I forgot to show that. It's from here. The supply filtering, there's a feed-through capacitor with some ferrite inside, so it's an inductor also, good for very high frequencies. Then another inductor, 2 microhenry or something, and a diode for protection for reverse voltage. Then a big electrolytic, 6,800 microfarads, and a high frequency capacitor, a 7812, and then another high frequency capacitor and another big electrolytic one, 6,800 microfarad, 10 ohms and then 10,000 microfarads. And this point supplies plus here. And this 1 ohm resistor is to prevent a resonance between 0.33 microfarads and the inductance that this capacitor shows at some frequency, I don't know where, but I want to kill any possible resonance by this resistor. 22 ohms in the sources give about 15 millihertz per transistor, 15 milliamperes per transistor. Here is what it looks like on the network analyzer. The frequency span is 10 MHz and the center is 10 MHz. So it's fairly close to optimized for 10 MHz, where I will do measurements on this in the interferometer. Here is a two-tone test. The 2 signals separated by 100 kHz, and I have set the level where the intermodulation signals are about 20 decibels below the 2 tones, and each tone on the output is plus 22 dBm, which means that the peak power is 6 decibels above. That's plus 28 dBm, and there is a considerable amount of compression because the third order is pretty strong. So I reduced the signal levels by 6 decibels on both generators, and then you can see that the output is 18.8, that's 19 dBm, peak power plus 25, and at this point the intermodulation is not very strong anymore. So that's the power aspect of the amplifier. I have connected this noise head, and it's cold now, and I have calibrated Linrod at some arbitrary and fairly large bandwidth to show 0, as you can see, 0.00 something. And I switch on the noise head. And it isn't perfectly stable, it drifts a little bit in the beginning, but it's about 1 decibel, a little bit less. As you can see, it's on the low range. And here in Linrad I see not yet, but I see clearly more than a 3 dB increase of the noise. So the noise figure is better than 1 decibel. I see 3.1 here. So I try to reduce this a little. The potentiometer isn't. Now it says 0.75 approximately. 0.75. And I see 3 dB. So the noise figure of this unit is about 0.75 decibels. At least it is well below 1 dB. Next step is to look at it in the interferometer. I have done the usual calibration at an offset of 300 kHz from this generator, and I look at the signal with the SGR IP, which picks up what is present in one of the legs of the interferometer. And here I can see 80, minus 80.0. And when I click on the carrier here, and like that, I have it in the passband, and it shows 0. So the signal 300 kHz below is 80 decibels below the carrier. And then I look at the output of the interferometer, but I have to make balance proper first. Well, that didn't make any difference, and so far so good. So what I see is minus 80.0. And then I switch off. And now I can read the noise floor in a bandwidth of 1 kHz. And I think I should expand a bit here, like this. And the level is minus 154.9. Or once more, minus 154.9. And 30 decibels for the bandwidth means minus 184.9 dBc per hertz. What I see is really the noise from the device under test. I can show that by inserting attenuation at the output of the interferometer. And you see that lowers the noise floor a lot. So I don't have to take the noise of the interferometer itself into account. And I restore here, normal. Now the offset is 3 kHz, and I switch that signal on, and I look in the SDR IP at 3 kHz offset, and I read minus 80, and the carrier should stay unchanged. It's here. Yeah, it shows 0 as it should. So the signal is 80 decibels below the carrier. And in Linrad, the signal is here, minus 79.999. So I switch it off and look for the noise floor. And this is only 3 kHz now. And the noise floor I see is from here to here, minus 154.9. Means minus 184.9. I can read again, 154.9. So at 3 kHz, minus 184.9. These numbers are not statistically significant, I think. They differ by 0.1 dB or so, from 300 kHz to 3 kHz. Now I have to change the sampling rate for the persives before I can go closer. The separation now is 1 kHz in a bandwidth of 100 Hz. And I look at the noise. Oops. I was probably not quick enough for that. 164.5. That means minus 184.5. So maybe this half a dB is significant. I will step closer. In the range 500 Hz to 200 Hz or so, there is a lot of interference from the magnetic fields because of the computers I have. They interact with the BNC connectors because BNC has gold on nickel, and the nickel is ferromagnetic and sensitive to the magnetic fields. You can see about that in one of my previous videos, where a permanent magnet close to a BNC connector changes the signal that goes through it quite a lot. So I have to reduce the bandwidth and look maybe here. Something is microphonic, so when I speak you see vibrations causing all those sidebands, but I can keep quiet while doing the measurement. The separation is now 530 Hz, and when I start speaking you can see the noise sidebands due to that, but while I was not here I received a noise floor of minus 172.7, means minus 182.7, because the bandwidth is 10 Hz. And I will have to step much closer to the carrier to get away from these magnetic field modulations. This is 60 Hz separation, and the bandwidth is 10 Hz, and the level is minus 160.4. So it means 60 Hz minus 170.4. So I clearly see sideband noise from the amplifier now. Here is 10 Hz separation in a bandwidth of 1 Hz. And what I see is minus 159.8. Minus 159.8. So noise is increasing rapidly, and I will check at 1 Hz 2 Hz separation, so I click 2 Hz away from the carrier. Now at 2 Hz separation and in a bandwidth of 1 Hz, the noise floor I see is minus 151.7. Means 151.7 because it's 1 Hz, so it's dBc per Hertz. Now the filter I have, 10,000 microfarads with 10 ohms, has a corner frequency of 2 Hz. So this noise might well be because of the noise from the voltage stabilizer, the 7812. I have changed the DC supply filtering. Now it's 22 ohms and 20,000 microfarads. That will shift the corner frequency down significantly, and maybe that affects the noise at the frequency separation of 2 Hz. We will see. Now the frequency offset is 2 Hz, and the noise floor is here, Well, I have to wait a little. Things are very slow when the bandwidth is only 1 Hertz. Because the filter uses a bin bandwidth of less than 0.1 Hertz to provide a nice rectangular filter. And I have to wait a little bit more. At 2 Hertz I now see minus 149.9. Minus 149.9. This doesn't seem right. I have to check things. I look once again at 2 Hertz. And the first half of it here, minus 150.6. So that's a little between those two values. The balance is now like this, but it was much better when I started the measurement. I can look at the second half. Well, I cannot. I can look at here, minus 150.05. So it doesn't differ very much. Anyway, the conclusion is that making the time constant of the filter 4 times larger does not affect the noise significantly, which means that the noise that I see at minus 150, a little bit around that, at the separation of 2 Hertz, that is a property of the FET amplifier and not of the power supply feeding it. That's what I think now. With 3 decibels less power into the interferometer, what I see 2 Hertz away is a much lower noise level. I would expect a 3 decibels lower level, but what I see is something like, well, two Hertz away from the carrier at 3 dB less power. The noise is much lower than 3 dB as compared to the previous. I haven't changed calibration or so. So it seems, I mean, it says now minus 159. I had before minus 151 or minus 150. So performance is better at 3 dB less power. And I will try at even a little less power than this. So going from full power means attenuation 0. I had minus 150 or something. And now with 3 dB attenuation, I see minus 160. That is about 10 decibels. And I didn't change calibration, so the improvement is 7 dB. Then with 6 decibels attenuation in front of the interferometer, I see minus 162.6. It is almost precisely 3 decibels from here to here, which means that all the improvement has come already at 3 decibels of attenuation. So I do proper measurements here at close range up to the point where I don't see any improvement anymore. At wide frequency separations, I should see a degradation by 3 dB, because the carrier is 3 dB weaker, while the noise floor given by the noise figure of 1 dB should stay constant. And there shouldn't be any noise added by there shouldn't be any noise modulation added by the amplifier. We will see. The amplifier with 5 parallel J310 is very good. It's better than anything else I have looked at so far. And lowering the power from 13 dBm to 10 dBm improves the close range noise by about 10 decibels. And of course it degrades the wide range noise by 3 decibels, because the carrier is then 3 decibels weaker. I have plotted it in the same diagram that I have plotted the QBH 1297, and I measured that in several configurations, and also for that amplifier somewhat lower power gives a better performance at close range, and of course a worse performance as wide range. I have previously measured several other amplifiers. You can see here, and I remove, it's the same scales. So before, the best one was this BUK 75150, and then there was an attenuator, and then the AMC 147, and then a real disaster, the SPF 5043, which is an MMIC for microwaves, which suffers from very bad AM noise. I also looked at some other amplifier, the UTC 565, and well, you can look at the videos for more details. It compares if you have the present results here and this one here. So the 5 times J310 at plus 10 dBm input gives really good performance, and as compared to the oscillators I have access to, you can see here what I think my oscillators are. The blue line, that is the sum of the phase noise and the amplitude noise of 2 oscillators. So a single oscillator is 3 decibels below, or maybe 4, because the 2 oscillators are not quite identical. But still, compared with the amplifier contribution, this is very much bigger, except of course at very large frequency separations, where the oscillators are down here and the amplifiers are much higher, because they cannot handle all the power of that oscillator.